All right, so let's start up on our 2.2 to 2.3 notes. So graphs of functions. So our essential questions: how do graphs represent functions? How can you use a graph to evaluate a function? And then the parent functions we'll be looking at is the basic unstretched, unshifted, and unreflected form of a function. Later on, we're going to learn how to stretch and shift and reflect them, but for now, it's the most basic version. Next up, we'll talk about domain and range. So domain is the list of all possible x values, and the range is the list of all possible y values. And then vertical line test tests whether or not a graph is a function. If any vertical line hits the graph more than once, it is not a function. It means that for any input, usually x, there cannot be more than one output, which is usually y. All right, so on these ones, we're going to just do the vertical line test here. And so the vertical line test says just draw a bunch of vertical lines. If there's any vertical line that you can draw that hits the graph once, then it is not a function. So that would mean that yes, this one is a function, and no, this one is not a function. Because if I draw the line there, it does not hit it more than once. All right, domain and range here. So for domain, domain is the smallest x value to the biggest x value. So it looks to me like the smallest x value here is 1, 2, 3, 4 is right here at -4. They didn't show that as a closed dot, but I'm actually going to assume it's a closed dot, so I'm going to use a bracket there. I would always assume it's a closed dot unless they use an open dot. All right, and then so the biggest x value is over here, and that would be a 3. So bracket -4, bracket 3. The range, this is kind of the same idea, but low to high. So I would say that the lowest y value is right here at -1, and the highest y value is up here at 3. And so that would be from -1 to 3. Notice that the biggest y value does not have to be at the same place as the biggest x value. All right, I'm not going to do the domain and range on the second one because it's not a function. All right, next up is a very important idea here, evaluating functions using a graph. And so a lot of people don't understand how to do this, but I actually think once you do understand, it's pretty easy. So first of all here, it says f of a is the y value. So our answer is going to be a y value at the specified x value. So whatever is inside is really our x, and then what's our answer is the y. So f of -3 asks, when x is -3, what's the y value of the graph? And you can see it's right there at 0. F of 0 asks, when the x value is 0, where is the y? Where's the graph? And you can see it's up here at a y value of 3. F of -4 plus f of 2 asks, when the x value is -4, what's the y value? I'm going to say that that's -1 here. I meant it to be -1 at least. If you said -0.9, I can't really disagree with you there. So if you want to use that, that's fine. And then f of 2, what's the x value at 2? I think I meant for that to be 1/2 or 0.5. And so that one would be -1 plus 0.5, that would be -0.5. Once again, answers may vary a little bit on that one. I'd say if you got anywhere between like -0.4 and -0.6, you're fine, because neither one of those was super duper clear. All right, number 4, I did mix it up a little bit here because now you see that the 2 is not inside. So now that 2 is referring to a y value. And so where do we have a y value of 2? Well, if I draw a line there at the y value of 2, I actually see it would hit twice, right there and right there. So I'd say that x could equal -1 or 1. Notice when they ask the question this way, we can get multiple correct answers because there are allowed to be 2 different x values for the same y value. These other questions, that can't happen because there can't be more than one y value for the same x value. All right, next up on the other one here, so we'll start off with f of -3. So that's saying when x is -3, 1, 2, 3, where's the y value? Oh, and it's right up there. Shoot, I think I meant for that to be at 2, but I'd say that's probably closer to 1.8. If you said 2, that's fine. If you say 1.9, that's fine too. All right, so then the next question asks, when x is 0, what's y? Now that, I think, is very clearly at 2. And then next up, we have f of -4. So f of -4 looks to me like it is at right there at 0. And then f of 2, when x is 2, y is also at 0. So very difficult math there. 0 plus 0 gives me 0. Last question says, what c values does f of c equal c? So this one is asking, when is the x value the same as the y value is really what that's asking right there. And so as I look through this, and you guys maybe can do this on your own, try to find an x value that's the same as the y value. So I see it right here, and then I also see it right here. So at 1, c equals 1, the x, it's 1 comma 1, so the x and the y value are the same. And then at c equals 4, the x and the y values are also the same. All right, next up here, we have a parent function chart. This isn't all the parent functions in the world, but I just kind of did the 5 probably most important ones that we need to be kind of familiar with, and we can add to this as we go along here. So the first one is the constant function, and so this one would be f of x equals c, and so c would just be kind of any number. So it could be I don't know, it could be 1, it could be 2, it could be 1/2, it could be -5, it could be 0. And so anytime that happens, no matter what x is, y will just always be whatever that number is. So I'm just going to put c, 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 c. Just be careful not to get seasick. Cool. And it sounds like I'm saying yes a lot in Spanish. Okay, and so what this graph always looks like is a horizontal line. So whenever you have y equals a number or f of x equals a number, it's always going to be a horizontal line at c, wherever that is. So if it's at 2, it's at 2. If it's at -5, it's there. All right, so the domain and range on this, well, the domain is going to be from -infinity to infinity. I think you can see there that the arrows go forever left and right. And then the range, I would say, is just c. Because it never moves from there, so it's not like it starts and stops. It has that one position, so I would just do bracket C kind of on its own. All right, next up here is linear. Oh, and you know what? I'll put a little description here. Probably a good idea as well. So this one is a horizontal line. Okay, linear, I'm going to say, is a sloped line. It could be a positive slope or a negative slope. I know you guys have had a lot of experience with linear. So it's like y equals mx plus b. The parent function, though, is actually f of x equals x, or just y equals x. So that has a slope of 1 and a y-intercept of 0. That's the parent function. Now, all other linear functions, y equals mx plus b, are kind of based off of this one. And so on our table here, you can see that x and y are always the same. And so that creates kind of a line that looks like this. Once again, like I said, it's a slope of 1 and a y-intercept of 0. The domain on this one, you can see the arrows go left and right forever, so that would be -infinity to infinity. And the range would actually also be -infinity to infinity because it goes up and down forever as well. All right, next up we have a quadratic, and so the equation is f of x equals x squared. I think you guys have quite a bit of experience with this one as well. So anytime we square negative numbers, they do turn positive, and so our table is going to look like that. And so this one creates that U-shaped parabola that I know you guys are familiar with. And so that is technically the name of the shape is a parabola, but the name of the function is quadratic. So a quadratic function creates a shape called a parabola. For domain and range on this graph does go left and right forever. Now, does it go up and down a lot faster? Sorry, does it go up a lot faster than it goes left and right? Yes, but it never stops going left and it never stops going right. The range is actually restricted here. It is from 0 to infinity. So you can see on the graph there that there is a point at 0, so that's why I did it as a bracket. And then it never goes below 0 on the parent function. That can change as the graph gets moved around, but on the parent function it'll be 0 to infinity. All right, next up here is the square root function. So our parent function for that is f of x equals the square root of x. And so on our table here, I actually you can see I changed the x values on here, so I kind of picked these strategically. I picked them so that they would have nice square root values there, as you can see. And then I put -1 there to just point out that this is, of course, imaginary. So I know you guys know that that technically would be I there, but we don't graph I on the real number plane, and so we're keeping it real here. And so this graph is going to look like this. Now, the shape of this graph is a half parabola. Sideways. Half parabola sideways, and that's not a coincidence here. The squared and the square root functions are very much related. They're actually inverses of each other, which we'll talk about later, and that's why they look alike. Now, why is it not a full parabola on its side? Well, I think you can kind of imagine that if we had the full parabola down here on its side, it would fail the vertical line test, so that's why we're only allowed to take the top half there. Okay, so then domain and range on this one. Well, actually, if we use our domain rules here, we know that the inside of a radical must be greater than or equal to 0. And so our domain in interval notation would be 0 to infinity. We can also see that on the graph that it never goes to the left of 0 because of those imaginary numbers. We can see here that the range is actually also 0 to infinity. It never goes below the x-axis. So there you go. All right, next up we have our absolute value function. Now, is this a fun function to graph? I'd say absolutely. So our parent function is just the absolute value of x. And so we know an absolute value does not change numbers but makes negative numbers positive. So it's going to look like that. And instead of making that U-shaped parabola, this one makes a V. And so it's diagonal straight lines instead of those curved lines on the parabola. Okay. All right, so our domain here is going to be, well, I see the graph going left and right forever, so that's going to be negative infinity to infinity. And then the range would be bracket 0 to infinity. All right, last up here we have our cubic function, so that'll be f of x equals x to the third power. So the interesting thing about this one is that the negative numbers stay negative and the positive numbers stay positive. And so it slopes down very quickly and slopes up very quickly on the other side. I've never had a good explanation for what shape this is. The best I've come up with is an unfolded paper clip. So next time you see a paper clip, unfold it and take a look at it and tell me if it looks like a cubic function. All right, so the domain on this one is negative infinity to infinity. And then the range here is also negative infinity to infinity. Now, it definitely goes up and down a lot quicker than it goes left and right, but it never stops going up, it never stops going down, it never stops going left, and it never stops going right. So that's our basic parent function chart here. So it's good for you to just kind of be familiar with what these graphs look like and what their domains are. And especially as we get to more graphs as we move on, just having this baseline knowledge of what these look like is going to help. All right, next up we're graphing piecewise functions here. So for these ones, there's a lot of different techniques that people use. I have my technique here, which is I start off with a table. Now, if you ever get kind of really good at these and you want to do it without the table or you want to skip steps on the table, that's kind of up to you to kind of gauge where you're at. But I'm going to start off with this table, and the key to the table is the border number or border numbers if you have multiple. Now, in this case, I only have one border number. And so it tells you it right there. It is -1 in this case. And so that border number, I always go to my table about in the middle and I write it twice. And I'm going to write it in 2 different colors, kind of color code this. You'll see why we're writing it twice in a second. But so then above the -1, I'm going to write a couple numbers smaller than -1. So I'll go ahead and write -2 and -3. And then below that, I'm going to write some numbers that are bigger than -1, like 0 and 1. 3 numbers per color is probably sufficient. All right, so now what I'm going to do is I'm going to plug in all of these x values into the function. So for this one, I have 2 times -3 plus 3. So that's -3. Then I have 2 times -2 plus 3. So that's -1. 2 times -1 plus 3 is 1. Now, some of you may be thinking, hey, Mr. Berry, didn't you plug that -1 into the wrong function? That doesn't go in that function. It doesn't have the or equals to. When I have -1, I'm supposed to plug it into that one. That is absolutely correct when we're evaluating piecewise functions. However, when we're graphing, I still want to plug it in there, but we're actually going to show that I plugged it into the wrong spot, and I'll do that right now. To show that we plugged that into the wrong spot, I'm going to graph that as an open dot when I graph it. These other two spots are going to be closed dots because those were plugged into the correct spot. But -1 was kind of plugged into the wrong spot, so that's why it's an open dot. So you will only ever have one of these open dots at a border number. The numbers that are not in the border will always be closed dots. Okay, next up, I'm going to plug in these other ones down here into the other function. So 3 minus -1 is 4. And then 3 minus 0 is 3. 3 minus 1 is 2. And so these are all going to be closed dots. Definitely a closed dot not on the border. And then on the border, you can see I plugged it into the correct function there. So now I'm going to draw these. So we have -1, 1 is an open dot. -2, -1 is a closed dot. And then -3, -3 is a closed dot as well. And then for my red graph, I have -1, 4 right there, 0, 3, and then 1, 2. So you can see that we have kind of a graph on the left-hand side and a graph on the right-hand side. And so I'm just going to draw this graph on the left-hand side, and it's going to go left forever. It does not go right forever, though. It does stop. And then the graph on the right goes right forever. And that does not go left forever. It stops. I'm going to draw this really quick, but don't draw this. So a lot of people will extend this going that way. That's not good because you can see it fails the vertical line test. So that's why only the right graph goes right and the left graph goes left. You can see that the way I've drawn it now, it actually does pass the vertical line test. It also passes it right here because the open dot, the big idea on that is that it's not really there. And so it hits it once here and actually does not hit it there. This graph kind of stops at negative 1.000001. Okay. Now, how do people draw these without the tables? Well, you can kind of visualize here what this is saying draw this line if x is greater than or equal to -1. So if you know what this graph looks like, and this one would be a linear graph, a slope of -1 and a y-intercept of 3, you can see that that graph is going on there, but it only exists greater than or equal to -1. The graph up here has a slope of 2 and a y-intercept of 3, but only exists to the left of -1. So you can see that slope here, up 2 over 1, up 2 over 1. And although it doesn't actually hit the y-intercept, you can see that if it did continue, it would hit that y-intercept at 3, but it doesn't because it's only to the left of -1. All right, so now when they ask us questions like this, like f of -3 and f of -1 and f of 2, you actually have several ways to do this. So you can plug it into the table, you can use the graph, and you can use this table over here. So those are all really the same thing. It's 3 different representations of the same thing. So I think that's pretty cool. So f of -3, I'll go ahead and use the graph here. So then at an x value of -3, the y value is also -3. Although once again, we could have seen that in the table. So when x is -3, y is -3. And we could have plugged it in here and gotten the same answer. All right, next up, f of -1. Now that is right on the border. So definitely when we are evaluating a graph and we're on a border number like this, we would use the closed dot. And so that would be 4 right there. Remember, the big idea of the open dot is it's not really there. It's kind of like where would it be if it was there? So the closed dot would be the one we actually use. Furthermore, if we were to plug it into the function here, we would clearly plug it into here. So 3 minus -1 would be 4. All right, and then lastly, f of 2. It's not really on our graph, but you could see it would be right there. It would have the y value of 1. All right, for domain and range here, the domain on this one is, in fact, -infinity to infinity. There's no breaks in the domain. It goes forever left and forever right. Now, some of you may be thinking, oh, look, there's a break at -1 x value. It's actually not true because as soon as this one stops, this one kind of picks it back up. So whenever you have an open dot, closed dot on the same x value, that is not a break in domain. The range here, it definitely goes down forever. And so I'll say -infinity for that. But I don't see any y values bigger than 4. And so I will stop it there at 4. There's no breaks in the y values. So we're not missing any y values along the way. You could say we're missing 2, but it's actually over here. So we're not missing that. All right, next function here. Let's do another table and try this out again. we'll do our x and our y. And our border number this time is 0, so I go about to the middle and put 0 twice. Oh, let me color code this again. Okay, so we'll do 0, and we'll do 0, and we'll do some numbers smaller than 0, and some numbers that are bigger than 0. But in this case, you got to be careful here, because when we plug these in, they switch the order here. Greater than or equal to 0, you can see is up there. Less than 0 is down there. Usually they put them in the correct order, but it's not wrong for them to switch it like this. So I'm actually starting off down here on our constant function, -3. And so this one, there's no x to plug it into, so those are all just -3. Now, once again, here we have that open dot at the border. And so I'm going to show that there. Okay, and then up here we have x squared minus 3, so 0 squared minus 3 would be -3. Now that's a closed dot. And then we have 1 squared minus 3, which is -2, and then 2 squared minus 3 would be 1. Okay, so let's go ahead and graph this. Now, in this case, you can see that that the open and closed dot are in the same spot here, okay? And so that's kind of an interesting aspect here, and this does happen actually quite a bit. And so this means a couple of things. First of all, the closed dot wins. And so whenever you have that, it'll always be represented as a closed dot. I mean, it makes sense if you think about it. Remember, the open dot is not really there, right? It's kind of just a placeholder. So if we have another point that actually is there, then we'll go ahead and just draw that one. So we're just going to draw the closed dot. Okay, that's the first thing. The next thing, the graphs, the pieces are going to be connected. And so they're not always connected. They're not never connected. We saw on the last one that these were not connected because these y values at the border number are at different spots. But in this case, since they're at the same spot, the graphs are actually going to be connected, and that's okay. All right, so let's draw these points here. So we have let's see, I'll draw the red one first. So 0, -3, since that's our closed dot. And then 1, -2, 2, 1. And this one is going to go like that. It's a parabola. It's one of the quadratic functions here, x squared minus 3. And then we have it looks like we have a horizontal line going left with all these points at -3. Remember, I'm not going to draw the open dot at 0, -3, because it's kind of already there as the closed dots. And you can see those graphs are connected. Once again, once you get good at these, you can kind of see, okay, it's a constant function, a horizontal line at -3 to the left of 0, and then it's a parabola that's shifted down 3 as we go right of 0. All right, next up, f of -3, I'm going to use the graph is -3. F of 0 is also -3, and f of 2 is 1. And with those, I'm just thinking at -3, we're right there, y value is -3. At 0, the y value is also -3, and then at 2, the y value is 1. The domain here, I again don't see a break in the domain, so I'm just going to say -infinity to infinity. And then the range, the smallest number I see is -3. It is a bracket because it is included, but then it goes up to infinity. All right, now we have a 3-piece piecewise function. So for this one, I'm going to go ahead and make a table. I'm going to make it a little bit bigger here. And then I have 2 border numbers. So I need to write -2 is my first border number. I need to write that twice. And then my next border number is +2. So I'm going to write that twice as well. And we'll do some numbers bigger there. We'll do a number in between here. I only need kind of, like I said, 3 numbers in each set is usually sufficient. If you want more, you can. But I'm just going to go with 3 numbers in each set. So the first set is going in here. So it's going to be -3, -3, -3. The border number there is an open dot because there's no kind of or equals to, no line underneath, but the non-border numbers are not. All right, and then in between here, I'm going to plug these into that middle piece. 1 minus x squared. So 1 minus -2 squared. We're not allowed to go minus, minus, plus, plus there because of PEMDAS. So 1 minus 4 is -3. 1 minus 0 squared is 1. 1 minus 2 squared is also -3. Oh, and then those are this one's a closed dot on the border between -2 and x. This one's a closed dot because it's not on the border, and then this one's an open dot between x and 2. because we have no line underneath on that one. So open dot on that side, closed dot on that side. Okay, now we have the last one here, 2x minus 5. So 2 times 2 minus 5 is negative 1, and that's an open dot. Oh, and make sure you know here that, let me kind of separate this. So it's not a 30, that's just a 3 that's represented as an open dot. Okay, and then 2 times 3 minus 5 will be 1, then closed dot, not on the border there. 2 times 4 minus 5 is 3 with a closed dot as well. Okay, so let's draw this. So from negative 2 comma negative 3. Oh, actually, I see that once again here we have these two are connected. Same spot there, so I'm not going to draw that open dot. I'm just going to draw that as a closed dot. And then we have some blue closed dots going left, and we're going to have an arrow going left forever, but it does not go right forever because it stops at negative 2. And then in between here I got 0, 1, and 2 comma negative 3, and that's an open dot there. And this is going to kind of look like a parabola. I can see that it's a negative x squared in the function. Now the middle piece, if you have one, if you have a 3 piece, the middle piece has no arrows. So it doesn't go left forever, it doesn't go right forever. It has a distinct start and stop point. So this one starts at the x value of negative 2 and stops at the x value of 2. And then we'll finish it off here, 2 comma negative 1, we have an open dot, 3 comma 1, and then 4 comma 3, and that makes, looks like that, okay? And then once again here you can kind of see where this is coming from. So we have a horizontal line at negative 3 right there, to the left of negative 2. In between negative 2 and 2, we have an upside down parabola right there. And then greater than 2, we have a slope of 5, linear. Sorry, slope of 2, excuse me, linear, up 2 over 1, up 2 over 1. It would have a y-intercept of negative 5 if we extended it down there. All right, so then we got a f of 0. So f of 0 on the graph is right there. You can see it has a y value of 1, so I'll go ahead and label that. F of 2, very interesting here. Remember I said for these evaluating the function, we have to pick the closed dot. Now there is no closed dot, and so I'm going to say this one is undefined. And if we were plug it in here, there's nowhere to plug it into. It doesn't apply to either of those rules. F of 5, I don't have that really on my graph, so I'll plug it in. So 2 times 5 minus 5, is that 10 minus 5? That would be 5. All right, domain on this one. Now, in this case, I actually think we have a break in the domain. So I'm going to say this goes from negative infinity, and then it stops at 1 for just a second, and then, sorry, not 1, 2, and then picks up on the other side of 2 and then goes to infinity. Because there's no x value of 2, I have to show that on my domain that we're skipping over that number. So this one is saying the parentheses means it goes right up to like 1.99999 and then picks up at 2.00001. So we're just skipping over that one number. The range, once again, I think that'll be negative 3 to infinity like we saw last time. I think I see the smallest value, smallest y value is any of these ones. And then it goes up forever. There's no y values missing along the way, so it's negative 3 to infinity.